All right, good morning, everyone. This is Jeff Eisenman, and welcome to the Maverick Applied Science webinar series. This is our fourth webinar of the series entitled Solving Challenges to Reliability. We're going to do something different today is we're going to have an expert panel session. So we'll get into that. I'll kind of explain the details of that. So let me try to move it on. There we go. So let me introduce the panelists. A little bit about Maverick Applied Science. We were founded in 1999 as an independent FRP engineering company. The company has grown over the last 21 years and now offers non-metallic engineering services for FRP, dual laminates, thermoplastic materials, pipe supports, and inspection worldwide. Our focus is maximizing the reliability of non-metallic systems for our clients through providing guidance and best practices in material selection, engineering, maintenance assessment, and construction of these corrosive services. Again, my name is Jeff Eisenman. I'm the president of Maverick Applied Science, and I have over 30 years in the FRP industry. Also participating as a panelist is Tom Haber, who is our Quality Assurance Program Manager here at Maverick. Tom has 25 years of experience, or over 25, I should say, in the FRP industry and has been with Maverick for 9 years. And last but not least, Darryl Mikulec, who has been with Maverick for 14 years and currently directs our engineering group as engineering manager. So a little bit about the format today for our expert panel session. So I'm going to give a brief presentation. That'll be about 10 minutes or so, and then we're going to transition with some opening comments. And then following that, we're going to open it up to some questions to the audience, and hopefully we'll have a kind of a ongoing discussion. Then we'll tell you a little bit about our next webinar and closing. So how to ask a question once we get to that point. You have a control panel. It doesn't exactly look like this, but there'll be a chat box. You can either input your question in the chat box, or there's an icon there where you can raise your hand. Either way, you can ask a question either by text through the chat box or by raising your hand. So now we're going to get into some of the challenges to reliability. And some of the basic things that we see are, the first thing is outdated specifications. If your specs are more than 5 to 10 years old, they need to be updated. We learn a lot every year about details of execution, whether it be things related to tolerances, things related to design checks, or specific concerns related to materials, and those sort of things need to be built into the specification. So before you start any new project, think about updating your specs. And then next would be poor material selection. So this would be selecting marginal materials versus best materials. I understand there's a budget concern at times, but if you pick a marginal material and it doesn't last, you're going to cut your service life short. And if it leads to a failure, well, one single failure just costs 10 times more than whatever you might have saved on that material selection. And then moving on, a significant component that we see that might challenge reliability is basically insufficient engineering and analysis. And this can be engineering checks and reviews. In the engineering field, we expect every single document to be checked by at least two sets of eyes. Somebody does it, and at least one person has to check it, if not another. And also, you want to make sure you have qualified engineers doing the work. And then a lot of, particularly piping, tends to get installed by typical piping rules, and not by related to carbon steel, and not by FRP rules. So really, we need to follow good FRP engineering practices, and a lot of times that includes pipe stress analysis. And then the next concern would be related to quality, and that's quality that we see in manufacturing. That could be related to workmanship concerns, qualified laminators. Installation could be having qualified laminators in the field. Could be challenges with surface prep and bonding. Could be challenges related to weather, things like humidity and moisture, cold weather, too hot, those sort of things. And then finally, operational stability. When we design based on specific operational or design concerns, design temperature, design pressure, those sort of things. Upset conditions, instabilities in the system, it pulls the vacuum when it's not supposed to. Maybe the temperature spikes where we're supposed to operate at, say, 160 and the temperature spikes over 200. Those sort of things is what we're talking about. Water hammer would be another example of concerns with operational stability. So I wanted to talk a little bit about the cost of leaks and failures. This is something that really doesn't get talked about enough. Sometimes it's just data that nobody looks at, or maybe they don't collect it. But in our experience, in the plants that we go out to, generally what we find is the typical plant has unplanned downtime due to leaks and failures, something between 6 and 20 days a year. So in the span of a year, it doesn't sound like a lot, but when you look at lost production, depending on if it's a unit comes down, the entire plant, or maybe just one train of a unit, you can have lost production for that plant of anything between, say, $100,000 to $500,000 per day. So you lose a half a dozen days, and that way you're talking a lot of money adds up. And then all of a sudden, the engineering and inspection maybe isn't such a high cost. And that's not even including the cost for repairs, depending on what the repairs might involve. So wanted to talk a little bit about where we see the failures. So here at Maverick, we've been doing this, we've been collecting data and basically putting together this survey for about 12 years or so now. And some of the data probably goes back over 20. And what we have done is we've defined the failure and those influences that led to that failure. And usually it's not just one thing, usually it's 2 or 3 things. FRPs we find fairly forgiving for the most part. So if one thing's not perfect, then usually you probably still are doing all right. But if you have multiple things where you have deficiencies, that's where we see the issues. And the biggest one, as you can see here, is engineering. So this is design, this is upfront design, maybe lack of pipe stress analysis, maybe not doing checks of tank calcs from a vendor, those sort of things. And then after that, we see fabrication. So this is quality and workmanship. Again, could be qualified vendors, maybe not meeting tolerances, those sort of things. And then the next criteria here or category would be installation. So this probably relates largely to piping applications versus tanks and vessels. And again, this would be the challenges of having qualified laminators in the field. This would be dealing with field conditions such as excessive heat and rain and all those sort of things. And again, part of the aspect of the field also is that you want to have that inspector in the field as well, kind of keeping an eye on the work as well. And then the next category we see is material. So this relates to material selection. So this could be selecting maybe a marginal resin versus the best choice for resins, or with respect to dual laminates, this may relate to lining selection or welding material, that sort of thing. And then operational, as I mentioned before, these things are like upset conditions, water hammers, those sort of things. So you can see that there's not just, it's not all about workmanship, that the reasons for failure are touched by almost every phase of the project. So what I guess the real message here is that we need to focus on and to attention to detail in each phase to see it through to a successful execution. So some final thoughts. We're talking about reliability and what challenges that. And I would be remiss if I didn't say that there are numerous successful applications of FRP and other non-metallics all over North America and worldwide. Largely We do see success, but what the point is we can still do better. We have lots of room to improve, and what we want to do is, and I'll just kind of throw some numbers out, is if our success rate is say it's 88%, we really want to move that number to like 98%. So we want to knock out that last 10% of failures so that everybody has confidence all the time in FRP, just like they would in any other metallic material or other material in their plant. And again, it's all about basically paying attention to detail in each phase of the execution plan from start to finish. And last thought to leave is that in our experience, most leaks and failures are preventable, if not almost all of them. So if you're experiencing leaks and failures, they shouldn't be expected and they shouldn't be accepted. And there's definitely a path and a plan to execute well to eliminate those. So now we're going to transition to our Q&A time, and Darryl will take over with that, and you'll be seeing us soon.
Hello, everybody.
Morning, everyone.
I am Darryl Mikulec. I'll be the moderator for this session. So if you see me kind of looking away, it's because I'm sifting through the questions and kind of looking at the attendee list. This is Jeff Eisenman to my left here. He's the president of Maverick, and then Tom Haber all the way to the other side, far away from me. We have all been recently tested for COVID, and at least one of the three of us has had it and has antibodies, which is me. And Tom has had every germ known to man, so he's pretty okay.
Those things won't eat me.
So, like Jeff said, this is our fourth webinar. We've had 3 previous ones. You're free to ask any questions on the previous webinars, maybe that we didn't get to or answer sufficiently in your opinions, or you have the 3 of us with 70 years plus combined FRP experience for the next 45 minutes or so. So, you have our captive attention. If you ever had a chance or a tough time getting a hold of Jeff, now is your chance for the next 45 minutes to ask him any question that you want. So we're happy that you're here to join us. We'll try to be brief, but comprehensive. Kind of depends on how many questions we get. We're going to try to get through as many as we can. The ones that we don't get to, we will follow up with you personally. And some questions, maybe you'll stump us. Maybe we don't have all the answers, and we'll get in touch with you personally. But just kind of a reminder, you can ask a question in your chat. If you have a specific question for one of us, you can kind of lead off with for Jeff or for Tom or for Darryl, and we'll ask those questions specifically to them. Otherwise, just ask your question. If you would like to raise your hand and ask an audio question, we have that ability. So just raise your hand. I will call on you. Just know that it won't be anonymous at that point. We will have to show your identity if you're going to ask a question like that, but that way we'll turn you on and make sure your mic is on. You can ask a question and we'll answer it that way. So without further ado, we're going to get started. But in the meantime, while we're going to compile some questions here, I see them coming in. I'd like to kind of get Tom and Jeff's opinions here, maybe about their personal experiences. Jeff from a design and engineering perspective, and Tom from his fabrication installation experience. Just maybe your experiences with what Jeff was talking about in his pie chart where he showed all of those failures, and maybe talk a little bit about the obstacles that you guys have encountered just in your experience. So maybe Tom, start with you.
Okay. Morning, everyone, again. So for me, one of the frustrations I see with non-metallic equipment is it is specialized equipment. It is unique. It is very much similar to a specialty alloy piece of equipment. And yet, a lot of times, fiberglass and dual laminate equipment is almost treated as a commodity. You have your 3 or 4 vendors you've been going to since God created fiberglass. They're on your bid list. You go to them for everything, whether it's a tank or a pipe, and they're going to offer you because they're going to partner with someone else if they can't make what you want them to make. And so sometimes you don't get what you want. So for me, anyway, you need to constantly go through your vendors, make sure who is responsible for what, who is good at what, and then do your due diligence during the fabrication. Make sure that the resin used was actually the resin used. That can be a simple thing of checking paperwork. So many of the QC oversight functions that you can perform as an owner are relatively simple with a little bit of guidance and just knowledge of what to look for. You can do quite a bit of due diligence to just make sure that you're getting what you want. And then once it's in service, to make sure that that piece of equipment will deliver operational success for you. So that's the goal: safe, successful operations of all your non-metallic equipment and giving you additional confidence in that non-metallic equipment. So, Jeff, design side.
Sure. So we have the opportunity to get into the field quite regularly, and a lot of times we're asked to come out and talk about a piping system that may be having problems and may be problematic from having multiple failures over time. And largely what we see is we'll go out on a site and first thing we'll walk it down and it's like, okay, well, here's this failure, this happened 2 months ago, and here's this one happened 6 months ago, and you're just going around kind of taking it in. And the first thing you look at as a piping engineer or an FRP engineer is you're looking at the route, you're looking at location of pipe supports, what kind of pipe supports are in place, the condition of the supports. So the most obvious things that you see is the pipe supports, and what we start to look at is, well, particularly hangers. For some reason, there's a problem with like clevis hangers, for example, where the bolt will have come off, or the nut will have come off, and now basically the pipe is supporting the hanger instead of vice versa, where it's just kind of hanging off the pipe. These are simple maintenance things that can be cleaned up, but for some reason they don't seem to circle back too often. And then beyond that, we start to look at the movement of the pipe. And what we find is where we'll look at where the failures were, and then we'll walk down the pipe, and we'll see that maybe it's like just U-bolt after U-bolt after U-bolt after U-bolt. So there are no real anchor points. The guides are everywhere. A lot of times we'll even see elbows which are kind of bound up because they don't have a U-bolt on this side and a U-bolt on this side. So that elbow is really not able to flex. Generally, I mean, there are some best practices for FRP piping engineering, but a lot of times when we're talking about chemical service, particularly any service that's over about 150, 160 degrees Fahrenheit, these need to be analyzed with a thermal pipe stress analysis program, and that's what's going to define your supports properly to where you get the right support in the right place. And then beyond that is installation issues. From the standpoint of maybe shear collars have not been put in place, those sort of things. So that's the things that we see from the design standpoint is that follow through from actually executing some analysis in advance to actually following through and with the drawings in the field.
Thanks, Jeff. Okay, first question. This one's going to be for Tom. Question is, what is the best tool that you know to spot or prevent leaks in vessels? And I guess this could go for also piping as well.
Sure, any of your non-metallic equipment. So the best tool I know of to spot leaks is your eyes, honestly. I mean, there's a number of mechanical tools that can tell you the structural integrity of a vessel, things like that. But the best tool for spotting a leak is your eyes. The best time to find those leaks is when your plant is operational also. So you need the plant to be out in your plant. I know a lot of times inspections are only done during outages and things like that, but external inspections of vessels and piping and non-metallic equipment should also take place during operations, during normal operations. I'm sure none of you have an extra spare day in your schedule where you can just walk around your areas, but try to find that time while it's operational and look at the equipment. See when your pump cycle on, do the pipe shake? See when your pump cycle on, does your tank bulge? Things like that that you would only find when the plant is actually operational. So as important as inspections are during outages and to make sure that the mechanical and structural integrity of your equipment is good and sound, it's just as important to keep an eye on it during operations to make sure that your operations aren't inducing unexpected stresses into that equipment.
So a follow-up to that question, Tom, is what's a good rule of thumb for internal equipment inspections?
Well, assuming that that means frequency or regularity, that's a difficult question to ask because it's not as simple how long will the fiberglass tank last, because a fiberglass tank lasts different times in different services. If you have a very aggressive service and a very demanding chemical being stored, and it's a high pressure storage tank, it's a much different inspection situation than an emergency water storage tank that only sees water stored for 5 years. So the inspection frequencies have to be based on your plant operations also. We like to use risk-based inspection frequencies, which go and include the plant operations, the criticality of the equipment, the dangerous nature of the fluid being stored, and then, just how important this is inside the plant, if it's very difficult to replace or something like that. And all those factors go into deciding how often a vessel or a piece of equipment should be inspected.
Appreciate it, Tom.
Okay.
We'll ask this one to Jeff. Jeff, what's your position about positives and negatives comparing ASTM D3299 and ASME R2P1?
Okay, so I've been attending ASME RTP1 committee meetings since about 2000, so about 20 years. Here at Maverick, we're committed to RTP1. So, that is kind of our general preference, but I guess there's a broader discussion. Generally, when we start talking about 3299, it's an ASTM standard that's probably about 18 pages or something like that. And we're comparing it to RTP1, which is about 200. So there's a substantial amount of difference. It's not just about design factors and design formula. It's about material selection and material qualification. It's about design validation. It's testing of laminates. It is testing and inspection of the actual equipment. It goes into far more to qualify the materials, the design, the execution, and fabrication. You're really not going to get that in 3299. 3299, the typical conversation is, well, we need something for wastewater tanks. Sure, and that's fine. Particularly in oil field, we see a lot of just basic water tanks that are collecting dirty water and things like that. But if we're talking about chemical processes, and that's the thing is, typically we're talking about corrosive chemicals, which are also very hazardous. We're talking about HCl, sulfuric acids. We're talking about caustics, things like that. These, if there's any kind of a failure, you have a substantial exposure to personnel as well as damage to equipment and performance of the plants. So if we're talking about chemical service, I really think that RTP1 is the specification that should be used.
Yeah, and if I can add, there are great many positives to RTP1, and we have presentations, and that may be a future webinar topic of the merits of RTP1. That's a whole topic in itself, but 3299 is limited to plus minus 14 inches water column, so it's generally an atmospheric tank standard, pretty bare bones. There's no requirement for there's a low minimum requirement for axial strength, and that's fine for a storage tank. It's hydrostatically loaded, hoop strength is important, axial strength not so much. There's a difference in the design requirements for RTP1 versus 3299 that ensures you have to meet a minimum strength, and that usually goes in the form of adding unidirectional strength to your shells, to your laminates. If you're just doing an atmospheric storage tank, you can get any number of weak, efficient wind angles that the fabricator can do quite inexpensively but it is very weak and can't be put in just any service. So the next question I have here, Tom, you can take this away. It's regarding AE testing, acoustic emission testing. Do most of your clients use MonPack? And maybe just give a little background of what AE testing is.
Sure. So acoustic emission testing is a passive system, basically. It is an NDT, although it does require some stress be induced into the tank in the form of a hydrostatic pressure, typically. So, but it's a non-destructive test. AE will listen using a variety of sensors around the vessel or the equipment or the piping, and it will listen for fiber breaks or delaminations or other noise that is significant. So the MonPack software was specifically developed by Monsanto and Physical Acoustic Corporation. So that's I don't know how proprietary, honestly, that is, but it is used fairly regularly out in industry. Other end users do have their own requirements that they'll use occasionally, but MonPack is a fairly common standard that's used for acoustic emission. Typically, there's also requirements in RTP1, I believe, and also ASTM E1067, and also ASME Section 10 regarding acoustic emission, so there's additional information in there. It's not as widely used as some of the other non-destructive tests, but it is very effective in finding structural irregularities and can be a very good tool for determining the structural capability of the remaining vessel of laminates.
So Tom, would you say about a third of the tanks that we see when they're hydro, they use AE?
Yes, a third is probably a good number. It depends. We go through phases where we'll have a project or something where that project will require, and so that brings a lot of AE vessels into our inspections. But typically, it's roughly between a third and a half of our workload is inspecting vessels that are going to be AE tested.
All right, Jeff, can you talk a little bit about expected lifespans of FRP piping and various services?
Sure. So it's very service specific. So it depends on pressure, temperature, but more specifically, chemical concentration, what chemicals we're talking about. So if we're talking about a mild service, like something that's going to be just a mild, salt or base, some of the FGD applications, or something that's going to be, say, sulfuric acid, even though doesn't appear to be mild, we would typically see something approaching 20 years out of a sulfuric acid service. If we're talking about like seawater cooling, for example, like in a power plant, there are systems out there that have been in service for 40 or 50 years now. So for seawater, it's a very good application. If we're looking at something like HCl, you're starting to get more and more challenged by the chemistry, and you're probably looking at 15 to 17, 18 years is pretty typical. Sometimes if really everything is done well and you get the best resin, the best fabrication, best design, maybe you might push it to 20, but that's probably something close to the limit. Chlorine applications, chlorine dioxide, for example, chlorine gas. Generally, that's probably the most demanding service because it actually is attacking the FRP, and even dual laminates, they have their limits. And in that kind of situation, if it's FRP and we're talking about a typically kind of wet gas service, kind of minimal concentrate flowing through it, you're probably something in the order of 15 to 17 years. And it's going through the corrosion barrier. The corrosion barrier is probably something close to ½ an inch thick. If you have more condensate in the bottom, what will happen is you'll get this little stream going through the bottom, and it'll actually kind of just basically you'll see corrosion, erosion, where it'll corrode it and then wash away the corroded material, and it basically just cut a hole through the bottom. And probably when you see higher condensate levels, you're probably closer to 10 to 12 years maybe. That's probably the most demanding service, I would say. But in most applications, outside of those couple that I just mentioned, generally we're looking at a 20 plus or greater life is what we really design for, and that's what how we want to select our materials as much as possible.
Okay, I have kind of a two-part question. I'm going to try to paraphrase. This is basically for Jeff. We have somebody asking about kind of longevity, what you were just talking about, but if they had a spec that wanted a 20-year, 25-year service life, and now they're at 30 years, and now they're starting to see issues, maybe the process changed, something like that, you can talk about that. And then the piggyback on that is maybe discussing, somebody want to know about 2992 and how that relates to FRP and how that can predict strengths and how we get some of our design factors. It's a lot there, so I'm just going to sit back and
Right.
Okay, so I guess let's take the first part. And so we have a service that was more or less designed, or expectation was 20 years, and you've got 30 out of it, and now you're seeing upset conditions, or you're seeing leaks and maybe some breakdowns. And I would say right off the bat, obviously a lot of good things were done in the beginning. If you got 30 years out of any chemical service, particularly, like I said, if it's seawater or something, well, that's expected. But out of a chemical service, you're getting 30 years, you got your money's worth, and you should be really happy with that. So what we find at that point is if you want to try to maximize that, is you need condition assessment. So we need to go in, and whether we can walk in it depending on what size it is. If we can get inside it and actually lay eyes on the interior of it, that's where we can kind of determine what the remaining life is. If it's a small bore pipe, then really borescope is what we would want to use to try to assess what's the condition of the corrosion barrier, the internal laminates, things like that. And then from an above ground piping standpoint, walking down the outside and basically doing support audits of what do the supports look like? Are they in good condition? We look at the pipe for signs of movement, so that you'll see where the supports will slide across the steel. And so you'll see a line on the support where it's kind of scraped across there. And so you can get an idea of, is it moving just a couple inches here or there, or do you see points where if you have higher movements and maybe should be more and more concerned in those areas? Maybe we want to reanalyze to make sure that the analysis that was done in the first place was done properly. Say half the analysis or systems out there probably weren't analyzed formally with stress analysis, that they probably did some form of application of rules for piping. So that's what I would say there, to try to one, identify, are you at risk yet, or is it still going good? And then, if from a condition standpoint, is we want to kind of, maybe it's time to take a look back and make sure from a design standpoint, because if it's 30 years old, well, we didn't know as much 30 years ago as we do today. So we might be able to sharpen it up to actually squeeze a few more years out of it for you. With respect to 2992, the ASTM standard for piping. So this is basically a long-term test program. Generally, you're testing, I think, a minimum of 18 piping samples, and you're putting them under pressure, and you're basically either cycling them from a pressure standpoint, or up to 10,000 cycles is what the intent is. So this is it's a very good test. It takes about 15 months to do it, so you can't do it for every system. The challenge is it's material specific, so that it's specific for that pipe, that resin, that glass. So if you change the resin, well, really the results of that test aren't really applicable anymore. You have to do it again. So for those manufacturers who have kind of commodity type of offerings, where they have, this set vinyl ester at this pressure rating, this set epoxy at this pressure rating, and so on. They've done that test and they don't change the materials, and it can work fine. What we see is, for example, in some of the ISO or EN standards, 14692 is referenced, and it requires this 2992 testing. But if it's put in chemical service and it's not the materials that were specifically tested the first time, well, really their data is not applicable. We find that truly very few manufacturers across the industry have this data, specifically for the products that they're looking to put it in today. So that's kind of a challenge with 14692. But I should say that ASME has put out and published a new standard last year. It's called NM2 for FRP. And this actually gives the manufacturer 4 different paths to qualify their product specific for those materials that they're using. And then it gives you basically a design basis to build on that they can justify their product and manufacturing processes. So I would say, if we're talking about chemical applications, that might actually be a better choice for a standard than the 2992.
Thanks, Jeff. We had somebody asking, and this is for Tom, maybe does Maverick have, do you personally have maybe a list of manufacturers, installers, whoever in the FRP industry that you would recommend based on past experience?
We can do that for you. We do a lot of work in a lot of different places, and we are able to work with a lot of different fabricators, a lot of different high quality fabricators. So, but what typically happens is fabricators can be specifically good on specific things. Some are very good at Kynar welding, some are very good at fiberglass welding. Some are the best manufacturers of fiberglass tanks in the world, but they don't go out in the field and install them properly. So the vendors list is a difficult thing to provide because it separates itself by piping or equipment or vessels, and each vendor has strengths and weaknesses for each type of thing. If you're going to buy 10,000 feet of pipe, I wouldn't recommend you go to the best tank manufacturer in the country, just because that's not their strength. So yes, please contact us. We'll be happy to help you with a better understanding of what your project is you're looking for, whether it's a vessel, a scrubber, some piping, a piping system, or whatever, dual laminate or FRP. And from there, we can help guide you toward a list of fabricators who have manufactured that equipment before, and we know are substantial fabricators. And then from there, you've at least narrowed down your list of vendors to qualified vendors, and then from there, you can make an equal choice between them.
Yeah, and there are also, maybe you mentioned this, maybe I was looking through questions, but there are also ASME RTP1 certified shops.
Absolutely.
And where can they find that?
Yep, if you want to buy a tank, a storage tank, and even if you don't need it stamped, an ASME certified RTP1 fabricator is a good place to go. It's a good vendor to use. And you can find that information in Google, I'm sure. I don't know if I copyrighted anything there, but you can just Google ASME, certified fiberglass RTP1, and it will bring you up a list of the current vendors who are certified by ASME to provide RTP1 certified vessels. And that's always a good starting point for vessels. For piping, it's a little bit more difficult. Sometimes that's even regional.
Okay. We have a question here. I think maybe I'll expound on it a little bit. Has Maverick ever looked at fiber orientation in relation to thermal expansion? In other words, expansion difference if fibers are all oriented parallel versus transverse. Yeah, I mean, there are ASTM standards for determining coefficient of linear thermal expansion. There are also laminate analysis software that is widely available, commercially used. There are several different options, and generally that's what we do if we're trying to predict thermal expansion. But yeah, most definitely, the resin, the more resin content, the higher the expansion, the more glass you have in the direction that you're worried about. So say you have axial direction glass, well, your thermal expansion is going to be lower comparatively in the axial direction versus if you had glass maybe helically wound at 55 degrees or some sort of a, unique laminate sequence. So yeah, the glass in the direction of the expansion will definitely reduce the more resin you have. So there are different laminates with FRP. The standard ones are type 1, 2, and 3. 1 is all contact molded, just chop strand matte. That's very high resin content, about 70% resin. So that's going to expand a fair amount, somewhere in the order 18 to 20 to 22 times 10 to the negative 6 in US units. You have type 2, which is alternating matte and woven roving, and that's going to be somewhere around 35 to 40% glass content, so about 60 to 65% resin, so that's going to be a little bit lower expansion. And then your higher glass content is with your 55 degree, your type 3 laminate, and that definitely expands the least amount. But yeah, if you throw some unis in there, so glass in the direction of the growth, then that's going to be your actual lowest thermal expansion. So we haven't done any physical testing. There are ASTM standards out there for that, but laminate analysis software calculates that pretty accurately for you as well. Now I'll throw one to Jeff here.
You actually have some questions on the side that you want to let some.
Those are the people that are asking these questions.
Okay.
Yep. So Jeff, are more leaks, and this is based on your experience, maybe the pie chart would speak to this, but are more leaks caused by over torquing or inadequate pipe support?
Well, leaks are caused by both issues. Let's put that out there. I would say more times the issues that we see related to the leaks and failures that are observed are probably due to deficient design and improper supports more than over torquing. But from an installation standpoint, over torquing is probably the biggest issue for FRP flanges, whether it's tanks and vessels or piping. Majority of leaks that we see are and failures that we see are because basically they don't use a torque wrench. That's the first flaw. Is they're not using a torque wrench at all. Then it's, you know, it may be that maybe it doesn't seal for the defined value, so they bump it up. And a lot of times that may have something to do with the gaskets that we're selecting. So we want to have softer gaskets so we can seal easier. In some chemical services, that can be a challenge, but they're coming out with new gasket these days that are much easier to seal at lower torques, so that becomes less of an issue.
Okay, we have two questions talking about abrasion resistant additives. Somebody's actually having a little bit of difficulty with their abrasive slurry. Tom, can you comment on maybe the standard abrasion resistant additives, if there's any other ones out there, any new developments that you know of?
Sure, there are two typical additives that are used for abrasion resistance. One is silicon carbide, and the other is aluminum oxide. And I do not know a preference. I think they've both been tested to work well, depending on the laminate. A lot of times it depends on the fabricator when you get to abrasion resistant materials, because abrasion resistant materials have to be well mixed. They have to remain well mixed in situ. They don't want to remain well mixed because they want to come out of the solution before you can catalyze it. Even once the resin is catalyzed and they're applied, sometimes they want to try to come out to the surface, which can cause air voids and spots. So if there's clumps and it's not mixed well, so there are no new that I'm aware of, but I can do a little research and try to find out and get back to you. Additives that will increase abrasion resistance. From what we've seen, a lot of times, if you can improve your fabrication and your expectations of what you're getting, then you can improve your service life that way.
Thanks, Tom.
Okay.
This could be a question for all three of us, just based on different experiences, and we'll see where this goes. But which failure mode do you see most in FRP, and what is the cause of this failure mode? Maybe Jeff started off.
That's a tough one.
We're talking about different failure modes and maybe
Piping
to
the vessels.
expect.
Yeah, in vessels, I'd say we see a lot of cracks in the bottom knuckles, and we see failures and cracks at nozzles, which may be from external loading from connected piping, for example. That would probably be the biggest thing. When we're talking about from design checks, that bottom knuckle usually when we find that it was maybe too thin, or maybe there's more loads there than what were anticipated as a standard storage tank, and maybe it's got some internals in there that are hanging on the sides. Maybe it's extraordinarily tall, so the vertical weight of the shell is more. Those sort of things are what we see from a tank standpoint.
And then from my perspective, I see a lot of mechanical damages, honestly, on vessels and piping. You see a lot of times where a come along is hung from a fiberglass pipe and it's used as a temporary support or something. Fiberglass pipe's not meant for that. You'll see somewhere where a forklift is backed into a tank or something like that, or a vessel has drawn vacuum and it wasn't expecting to. So there's a lot of different failure mechanisms that we see, unfortunately. I think sometimes our views are a little tainted because we're involved in failure investigations and stuff that sometimes we see more than the average person does. It's a good thing and a bad thing, but we don't see a lot of just wholesale fabrication issues. We just see a lot of long-term running issues. Maybe your process has changed, something like that.
Yeah, and just from a general perspective, FRP it's a non-ductile material. It's a brittle failure mode. On the other hand, it's a very forgiving material if done right. So there are design factors that should keep everybody careful in a safe range, but there is no yield point. When it gets to yield, it breaks. Failure mode is brittle. You know, that doesn't speak to joints necessarily. Adhesive joints sometimes have issues. That's different than the FRP material itself. You're looking into more maybe bending issues, maybe poor workmanship or surface preparation on joints. So there's not one single failure mode. It depends on what specific component you're talking about. But just in general, failure mode, brittle fracture is, you know, what you see with FRP material.
One more thing I want to bring up, Darryl, you reminded me of. A lot of times on a piping system, you'll see a piping system that's been well engineered, well designed, well procured. Everything is done right to the point when it arrives on your site. And then you hire a contractor that doesn't have a lot of fiberglass experience to install that pipe. So the final tie-ins on your $1 million system are made by a contractor that doesn't have the same level of expertise as the fabricator that built the pipe. So you may see errors from your field room. So it's important to me to remind people that you make sure you use qualified people all the way through the process of the installation of your vessel, including on your sites, because a lot of times that's where failures occur when the final installation contractor doesn't understand the requirements necessarily.
Okay, I guess a follow-up, and this is to Jeff, but I think I'm going to throw it to Tom just because he knows about this. So what is the effective UV degradation on, say, long-run vent piping where sweeps include chlorine dioxide? So maybe what is used to prevent UV degradation, and maybe what do you see, and is it cosmetic? You know?
Sure. There are additives that are added into the resin in the final layers typically, which will reflect ultraviolet light. It can do a good job of reflecting ultraviolet light in laminates. In the end, there is going to be some damage from ultraviolet light to fiberglass laminates. From my knowledge, it affects the resin, it impacts the resin and basically degrades the surface resin of a laminate until the surface resin is gone, and then the glass is remaining on the surface, which is what you see in fiber bloom or sunbursting. But then that reinforcement reflects the UV. It doesn't continue to take damage. So typically UV damage is a surface phenomenon. It looks ugly, it can be repainted, but it does not typically continue through the structural wall of equipment and cause structural damages to your equipment. The chlorine dioxide vent service is another issue because that would bring about damage from internal, so you would want to always make sure that you inspect your vents as carefully as you can, because a lot of times a vent on a vessel sees a much different service than does the actual vessel storing them.
Okay. So back to Jeff, and I'll probably talk about it too, depending on what Jeff actually answers. But speaking of over torque flanges, this piques some people's interest that are watching. We see references for values based on bolting, design flange rating, and gaskets. What do you typically recommend for maybe bolt torque values or just well fastened flanges?
Well, there's not one answer for that. It's very specific to the gasket and it's specific to the size as well. In most, I'll say, process piping cases, generally we're going to see torque values from maybe as low as, say, 25 foot-pounds, maybe a little less even on small diameter pipe. Maybe up to 100 would be on the top side. Generally, you're not going to see almost anything beyond that unless it's really high pressure. Then you're going to be pushing it up, and really probably need to look at going to O-ring gaskets or versus flat gaskets. The challenge is, so I guess the point of that is generally the value should look fairly low compared to what you would be seeing compared to carbon steel applications. Generally, the numbers are fairly forgiving. You could probably bump most numbers up 25% without a concern to try to seal, because maybe maybe the flange isn't perfectly flat or the bolts aren't torqued perfectly and things like that. If you're going much past that, then you probably want to talk to the engineer, the design engineer who designed it, and ask questions about the gaskets. Make sure that you know what the gaskets that you have are based on what the design was, or maybe there needs to be a gasket adjustment there. But you know, they can be much. We can have higher torque values if they're required, but then it's a custom design. So that flange has to be designed for the specific gasket that's going to be used, and for the pressure rating and the torque values that are going to be applied. So as long as everybody does their part and you see through the design standpoint of it, then it should be fine. But there's not really a single answer for that.
Yeah, and to echo what you're saying, Jeff, I mean, gasket selection is huge. There are plenty of good gaskets out there that are, you know, I know PTFE is needed in a lot of situations, but PTFE itself is very, very hard. There are envelope, stress saver type gaskets that are good solutions. They give you the PTFE outside with more of a cushioning on the inside, and that definitely helps. But some people swear to using hard gaskets, and it presents a problem for FRP, because sometimes it'll work. You don't know why it's working, but you know, you may be cracking a flange subtly. You may be eating into the design factor, but hey, it torqued up and that's all you care about. So that's what your site's going to use from here on out. But if you ask us or some other engineer to verify that, they're going to say, well, you need either softer gaskets or thicker flange. And then it's kind of a battle back and forth between the owners saying they have this legacy experience with this gasket that's working versus theory that's saying it's not. There are options to maybe go with lap joint flanges, which reduce the seating stress area. Use it on the screen. Reduce the seating stress area versus a full face gasket. So that way you can focus more torque, get more pretension on a harder gasket in that case. The con of that is currently in North American standards, we don't have a design approach for lap joint flanges. We're left to either test or believe that a full face design simulates the same as a lap joint, and it's not apples to apples comparisons there. There are advancements in all three primary ASME standard committees right now between Section 10, RTP1, and NM2 for pressure piping. There are task groups formed that are kind of compiling their experience, their history, their knowledge, calculation approaches that they think would work, or maybe just testing approaches that maybe ASME will fund, so we can get a lap joint design standard. So that's really where we might need to go if owners are insistent on using harder gaskets. So like Jeff was saying, it's not a one size fits all. Just say 25 foot-pounds for, you know, 1/2 inch bolts and 30 foot-pounds for 3/4 inch bolts. You can't just say that, because it depends on the bolt material, depends on the gasket selection, ultimately the strength of the flange. All right, Tom, I don't know if you'll be able to answer this to your direct knowledge, but there's a question about furan and phenolics. So maybe just give a little bit of background on those resins, maybe your experience, maybe the pitfalls, difficulties, and if they are covered by RTP1 or Section 10 to your knowledge, or?
Yeah, I saw you pop it up a little bit earlier, so I was thinking about that. To my knowledge, those resins are not discounted from RTP1. You just have to provide design basis laminates and tested laminates. So in the case of RTP1, I think that they could be used or to provide an RTP1 vessel. For Section 10, that would be a little bit more difficult. Section 10 has additional requirements such as AE and resins. For instance, furan does not do well with AE because of the curing mechanism and the laminate. So that may not be a good test. So could it be designed and built to Section 10? Yes, it probably could. I don't believe it could be stamped because I don't know that it would pass the acoustic emission testing, either phenolic or furan, but it is feasible, I think. I don't think it's precluded.
I would agree.
Yeah, I don't recall. I do know there are specific MTI booklets that you can buy for furan equipment. My recollection is that had a high design factor of 15:1. This is us being honest. We'd have to double check on RTP1, and we will double check and get back to you to see if it is out of the scope. Ultimately, the burden of proof is on the designer, whether it's in the scope of RTP1 or not. If you need a furan piece of equipment, then you need furan. You need to design it to something, and the burden of proof is on the design engineers, and there are resources and references out there specifically for furan.
So we do sit on RTP1 committees. I personally sit on the Materials and Quality Assurance Committee. So if it was precluded, I think I would remember it, but I am getting old. There's gray hair here now.
Some here.
What's here is gray.
So we have time for maybe one or two more questions. Jeff, this might not be to the asker's satisfaction, but there's a question about blistering. So I know blistering is, maybe some people watching in their plants have issues with blistering and they don't know what's causing it. Maybe there are different causes. What do you do about it? So maybe talk a little bit about blisters, whether it's in power generation plants with chimney liner issues or in a chemical processing plant.
Sure. So depending on specific surfaces, blistering is kind of a variable phenomenon. With respect to power generation applications in FGD, for example, in ductwork and chimney liners, for example, I would say probably for what we have seen, the principal cause of blistering is usually something related to dry glass, to air voids in the laminates. That's probably some of the main things that we see that are most evident. Now, all that being said, if there are operating upsets, if we have temperature spikes and things like that, that can cause blistering too, that wouldn't otherwise reveal itself at all. If there are tiny bubbles, when we have these temperature spikes, they expand and they turn into big bubbles, and you can see that, and the blisters will continue to expand over time. But all things being equal, where everything is designed right and run right and all that kind of good stuff, generally it's a fabrication concern is the blistering that we've seen. Now, we haven't seen as much in FGD that is large areas. Usually it's localized areas where maybe the winding was dry at a certain area or something like that. When it gets broader, it's probably related to maybe multiple influences. With respect to chemical processing, probably a very typical place where we see blistering is with HCl applications and chlorine applications. And that standpoint, a lot of that is due to permeation, where you have a very severe chemical attack. It's getting into the laminates. Maybe it collects in a pocket, or maybe it creates a pocket, and then it will grow over time and it creates these blisters. And at times they will break open and crack and expose deeper layers of the corrosion barrier, even the structure at times. When we're inspecting equipment and we see this, depending on the application, our first thought is we're going to try to evaluate what is the depth of the blister. And probably the first pass, our first time seeing it, if it's not something severe, where it's broken open, we're probably going to mark it, and we're going to make a circle around it, outline it, and then we're going to say, okay, we're going to monitor this, and in 2 years when we come back, we're going to look and see if it is expanded, or maybe it stays the same. If we come back in 2 years and there's no change, really, you know, we don't want to take a grinder to a good liner. We don't have to, because once we start doing repairs, we have secondary laminates, and they're never going to last as long as the original corrosion barrier. So we try to be very conservative in the choices we make before we just point to repairs. If we can, if there are imperfections we can live with, if we can live with them and not introduce any risk to the operation, we want to do that as much as we can.
Okay, I think that's probably a good one to end on. We want to be respectful of your time, and we had a number of good questions, and there's some that unfortunately we just couldn't get to, but we will be reaching out personally to be able to answer any questions. But we, you know, really just appreciate your time, you know, spending an hour with us. They're really good questions, good discussions. Jeff, do you have any final thoughts?
Just final thoughts. I'd just like to thank everybody for taking the time to share with us for this webinar. Keep in mind that we do these about once a month. So next month, Tom will be doing a webinar on shop inspections. So keep an eye out for that. And thanks again, and we hope to see you soon.
Take care, everybody.
Thank you.